Convolutional neural networks are the main way that we do image processing for STEM purposes. You might ask, why should students in this class learn about the basics of convolutional neural networks, like the inner mechanics? Well, it can help you know what abilities to expect a convolutional neural network to have and not have. So let's walk through a sheet from this spreadsheet. Here we're going to talk about kind of all kinds of image problems, not just segmentation. Suppose we have a microscope image of a yeast cell like this. This is a transmission electron microscope image of a yeast cell. And I've taken a cross section. I'm going to do a cross section here. I'm going to, I don't know if you can see the black line that was already there, but we're going to do a cross section here and just look at the pixel intensity values along that line from left to right. Let's scroll down a little here. So pixels that are almost black have an intensity value near 0. Pixels that are almost white have an intensity value near 1. And so here's the plot of the intensity values. You can see that on the left side of the image, it's background, it's fairly bright compared to everything else. So we've got intensity values that are near 0.9. And then once we cross into the body of this yeast cell, it gets darker, so the intensity values drop. And then there's this little section that looks almost hollow in the middle of the yeast cell called a vacuole. Don't worry about the vocabulary, but that's almost the same color as the background. So then the intensity comes back up. So what if we wanted our neural network to spot the edge of the yeast cell or edges within the cell? Let's consider a simplified version of this complicated graph. So I've typed some intensity values, just like 0.9 for background bright and 0.4 for inside the cell dark. And you could kind of compare this plot to like going from background to inside to background again. So we might have a thought of computing the slope from one point to the next. And we can compute the slope by doing something, and I'll start here, I guess. If we do this y value minus this y value divided by this y value, this x value minus that x value. So that's like y2 minus y1 over x2 minus x1. Um, uh, and don't worry if you're not getting the spreadsheet aspects of it. And we can tell it to do that everywhere. And we can't really do that at the very beginning, and for symmetry, we might not want to do it at the end either. There's various ways of taking care of that, but let's not worry about it. So we have also got those slopes that we just computed graphed here, and we can see that the slope is 0 when we're inside a region where the intensity isn't changing, like the background over here on the left or the background over here on the right, and also inside the cell where it's relatively dark but not changing, the slope is 0. But when we transition from a bright spot to a dark spot, we get a strong negative slope. And when we transition from a dark spot to a bright spot, we get a strong positive slope. So that's kind of saying, hey, there's an edge right here. So that's not a bad thing to do. And this formula might actually, if you've had calculus, but don't worry if you hadn't. If you have had calculus, it's kind of like a derivative. So that's fun. So that's not a bad thing to do. But it's a little interesting that here we're getting the edge signal happening once we've transitioned into the dark spot. And over here, we're getting the edge signal happening once we've transitioned into the brighter part. It's a little bit asymmetric. So we might want to do something a little more symmetrical. And one way we could do that is instead of using this pixel and the previous one and reporting that slope for this pixel, we could instead use kind of y2 minus y0 divided by x2 minus x0. So going one pixel to the left and one pixel to the right from this cell, that's more symmetrical, which is kind of a feeling. And now we're getting, again, 0 slope when we're in the dark region or in the light region, but at the edge, we're getting kind of an equal size signal for both before we step into the dark region and as once we're in it. And the same thing on the way out. So symmetry is nice every now and then. What if we wanted to smooth out some noise instead of detecting edges? Well, let's consider another set of simplified pixel values that could be a simplified version of just inside this dark part of the cross section. Um, what are some ways of smoothing out noise? Well, in statistics, we often take an average of things, right? So we could say we'll take the average of maybe these three pixel values and do that everywhere. And again, it's harder to think about what to do at the edges of the image, but don't worry about it. There's ways of dealing with that. And here we've got these red dots for the average of three. And would you agree that those bounce around vertically less than the blue dots do? So we've kind of smoothed out some of the randomness or some of the noise. So we just did two very different math operations, right? The slope is like subtract, subtract, and divide. It's like a quotient of differences or difference quotient. And just that's to detect edges. To smooth out noise, we took an average, and those two things feel very different from each other. But we'd like the computer to be able to decide which of them to do to give good results in making predictions, or maybe to do something kind of in between or even more extreme. So it'd be nice to have a more unified way of looking at them that would make it easier for the computer to adjust them. Let's rewrite them a bit. X2 minus x0 in our computation up here, like 4 minus 2, 5 minus 3, 7 minus 5. That was always 2, right? Um, and in the average, we were always taking the average of three things. So we're adding and dividing by 3. So the slope was y2 minus y0 divided by 2. The average was y0 plus y1 plus y2 divided by 3. So they feel a little bit more similar now. Or we could rewrite them as the slope being -1 times y0 to get that minus sign, plus 0 times y1, because we're basically ignoring it, plus 1 times y2 divided by 3. And the average is 1 times y0 plus 1 times y1 plus 1 times y2 divided by 3. So they're feeling even more similar to each other now. Or we could write it, we could kind of take the divide by 2, divide by 3, and rewrite that as a decimal, distributing it across the multiplying and adding. So we could say when we're computing the slope, like that's like -1/2 times y0 plus 0 times y1 plus 1/2 times y2, or the average is 1/3 times y0 plus 1/3 times y1 plus 1/3 times y2. So now it's basically the same math operations, multiplying and adding, but just with different numbers. This math operation is called the dot product of the multipliers with the pixel values. You don't have to know that, but if you've taken a class where you talked about dot product, it's nice to know that it's related. Um, so we could just boil this idea down to like, what are the multipliers that we want to use? For slope, like -1/2, 0/2, or for average, 1/3, 1/3, 1/3 maybe, and then let the computer adjust those sets of numbers to get better predictions. For example, maybe the computer wants to detect edges that face the other way, like left-right versus right-left. So maybe it would swap the positive and negative numbers in the slope here, for example. Let's try this computation of computing the slope by using the multipliers -0.5, 0, and 0.5. Here, so we did it before by typing a formula like subtract, divide, this other subtraction. But here, let's just try it. We're going to do this -0.5 times this number, plus this 0 times this number, plus this 0.5 times this number. And the key idea is, so there's a little bit of spreadsheet stuff here where I've had to lock my references to the coefficients, to the multipliers. Let me just show here. So there's the multiplication. If I copy that and paste it here, now I'm still referring to the same multipliers, but I've started referring to pixels that are one cell over, and then copy and paste, still referring to the same multipliers, but referring to pixels that are one cell over. So I can paste that over here. And this shows the results there. Now, this data set is kind of a noisy version of the background on the left, and a noisy version of the dark part in the middle, and a noisy version of the background in the middle, on the right. Um, So that's demonstrating that computation of using multipliers times pixel values and adding it all up. This idea is, and then we're doing that the same thing across the whole image. That idea is called a convolution in the AI neural network world. So a neural network that includes this idea is called a convolutional neural network, or a CNN. In an upper level math and mathematical statistics class, we use the word convolution, and it's almost exactly the same thing. There's one little twist, but don't worry about it. It's important here that we're using the same multipliers, in this case, negative 0.5, 0.5, everywhere across this image or this cross section of the image. So I'm not having to store a different set of multipliers for each pixel, for example. That would take a lot of memory. Um, we've been doing this for a horizontal cross section. We might want to do the same thing for a vertical cross section. And if we did, we might want to list the multiplier numbers vertically. But then we might think, well, images are actually two-dimensional, not just a left-right cross-section or an up-down cross-section. So then we might want a two-dimensional set of multipliers, which would be like a 3 by 3 grid of multipliers. I'll highlight the negative values in red and the positive values in blue. So if we're doing left-right edge detection like we were doing before, we might want a grid that's mostly 0, but with a negative 0.5 on the left middle and a positive 0.5 on the right middle. Or we could have negative 0.5s in the first column, zeros in the second column, positive 0.5s in the third column. That would kind of be using cells above and above, pixels above this row and below this row to kind of contribute toward that detecting an edge on this row. Or we could swap the positives and negatives to get an edge detector that kind of looks for edges the other way. For up-down edge detection, we could have mostly zeros, but with a negative 0.5 in the upper middle and a positive 0.5 in the lower middle. Or we could have negative and positive 0.5s all across the rows. For left-right averaging or blurring, we could just have like mostly zeros, but with 1/3 down in the middle row, for example. In the early days of CNNs, they used larger sets of multipliers, not 3 by 3 like this, but like 5 by 5 or 7 by 7. These days, people find that having 2 or 3 layers of 3 by 3 is often better than a single layer of a larger set of multipliers. I've said that CNN uses that set of multipliers everywhere in the image, but it also will have another set of multipliers that it uses to do another convolution, and might have a few dozen sets of multipliers that it applies to the original image to get a few dozen intermediate images. Some of those convolutions might be more like edge detection, some might be more like smoothing, some might be more like something even fancier. The best multipliers to use are figured out automatically during training rather than having humans sit down and try to figure out what the best are, which is what used to happen. After we compute a convolution on an image, we often then downsample it since we don't need all the original resolution, and keeping only the important parts makes the network run faster and take less memory, which is good. A common way to do this is called max pooling. So if we had a 2 by 2 block of pixels in an intermediate image like this, like 0.3, 0.5, 0.6, 0.4, and we do max pooling on it, we just report the number that is the maximum of those, which is 0.6 in this case. Um, uh, so that might be saying like this is what was standing out the most as an edge. If an image had a size of 100 by 100 pixels and we do max pooling on each block of 2 by 2 pixels, our new intermediate image will be half the size. It'll be 50 by 50. If we do that again, we'll get another intermediate image that's 25 by 25, which saves a lot of memory compared to the 100 by 100. Most CNNs do multiple rounds of convolutions, then max pooling. Each set of convolutions, then max pooling, is called a layer. This gives us many low-resolution intermediate images that each focus on a different feature, like an edge or a corner, maybe on early layers, or maybe a face for later layers. Then at the end, a logit score for each potential output category is computed from the most recent set of intermediate images, and then that is run through a softmax, for example, if you're doing convolution, if you're doing classification. Also, after doing convolutions, and max pooling, we often do a nonlinear function, which is kind of like logit, but we won't worry about that for now. All right. So that's our explanation of the basics of convolutional neural networks. There's a newer architecture for image processing called vision transformers, but we won't have time to talk about it. All the cautionary tales about gathering a good data set still apply to any newer architecture for doing image processing. So next, I'm going to send you to watch a video by Welch Labs that I really like. It's called The Moment That We Stopped Understanding AI. But some of it is more about large language models, which we'll talk about later. I don't want you to stress about those large language model parts of the image, parts of the video. So I've got a list here of what I recommend that you watch. And if you happen to watch the other parts too, that's fine, but don't stress about understanding them yet. So you can click each individual link here to start at the points that I'm recommending. The explanation of convolutional neural networks in this video is almost entirely about classification problems, which is fine. Like, does this picture contain a dog or an aircraft carrier or something? For image segmentation, we often use a CNN structure called a U-net, which you can look up later if you need to.